All right, now we're going to look at linear functions. So we just looked at functions, and it's a relation where each x value has one y value, each input has one output. Now we're looking at linear functions. So a linear function has two qualities. The first one is that it graphs as a straight line, as one straight line, and has a constant rate of change. It has a constant rate of change. Another thing that I want to point out is that it cannot be a vertical line. So it can be a straight line, but it can't be a vertical line. So we just talked about how a vertical line can't be a function. So if it's not a function at all, it can't be a linear function. Nonlinear functions have graphs that are not straight lines. So the rate of change is not constant. So values don't increase or decrease at the same rate. And we can look at that when we get to tables. So as you notice here, the last slide, this was a straight line. So that was a linear function. This one has a curve at the bottom and a curve at the top and goes in different directions. So this is nonlinear. So looking at this one, it curves, does not make a straight line, so it is not linear. Again, this one goes up, kind of goes flat, and then goes up again, so it's not linear. This one kind of looks like half of a U, not a straight line, so it's not linear. This one is just a straight line, so it's linear. And now we look at linear function tables. So there's two ways you can look at these. One would be to find your rate of change, and the second way could be you could graph it and see if it makes a straight line. So tables are linear functions if the rate of change for both x and y are constant. So here, my x's increase from 1 to 2, I add 1. From 2 to 3, I add 1. From 3 to 4, I add 1. That's constant. Then in my y's, from 2 to 4, I add 2. From 4 to 6, I add 2. From 6 to 8, I add 2. Because these 1's are constant and these 2's are constant, this is a linear function. So now we want to see which table represents a linear function. So I have to see how I get from one point to the next to see if they are constant. So if I look here, I have 0 to 1, I add 1. From 1 to 2, I add 1. From 2 to 3, I add 1. From 3 to 4, I add 1. Now if I'm looking at the bottom, I'm trying to see how I get from 300 to 285. And I do that by subtracting 15. 285 to 270, again, I subtract 15. 270 to 255, I subtract 15. 255 to 240, again, I subtract 15. So these ones, there's a 1 going all across the top. There's a negative 15 going all across the bottom. So A is a linear function. But I still want to look at B, the falling bowling ball, to see if that's a linear function too. So all across the top, just like the last one, I add 1, I add 1, add 1 again, add 1 again. Now we're going to look at the bottom So my h, this time h is my output. So how do I get from 300 to 284? I'm subtracting 16. Then from 284 to 236, I'm subtracting 48. So I can already tell this isn't constant. But from 236 to 156, I'm subtracting 80. And from 156 to 44, I'm subtracting 112. 112. So yes, my input is all constant, but my output is not. So it is not a linear function. So again, we're trying to see which one's linear, which one's not. These points are the same as, so your table is the same as these points. So back here, we looked at the rate of change. Here the next one we're going to look at if we plotted these points. So here we have 0 and 300. So 0, 300, plot that point. 1 and 285, 2 and 270, 3 and 255, and 4 and 240. So again, with the falling bowling ball, we have 0 and 300, 1 and 284, 2 and 236, 3 and 156, and 4 and 44. So if you are graphing these, you can just look at them and say, this right here makes a straight line. This one doesn't. So still, A is a linear function. So does this one represent a linear function? If I'm looking at my x values, I have a constant rate of change. But if I look at my y values, I have 9, 22, and 55. So this is a nonlinear function. Does this one represent a linear function? So I have in my x, I have a positive 3, positive 3, positive 3. In my y, I have negative 8, negative 8, negative 8. So these are the same and these are the same, which means this is a linear function. So linear functions with equations. So equations are linear functions if when graphed, they form a straight line. So with these linear equations, you can have y equals x plus 4, y equals 1/2 x. You can have y equals 4. You could also have something like y equals, I'm sorry, not y equals. So if I have 2x plus 3y equals 10. That could also be linear. Nonlinear equations, you can't have a variable alone in the denominator. You can't have an exponent. And here we have an exponent again. Another thing that you can't have are two variables being multiplied by each other. So if you had 3xy, x and y are being multiplied by each other, so that's nonlinear. So here, if we were to graph this one, if I had y equals x plus 5, this makes a straight line. So that means that this is linear. And it follows all of our rules. If we graph this one, So we have y equals 4x divided by 3. Still follows our rules. It's linear. Now this one, you have y equals 1 minus x squared. So if we graph it, we can see that it makes an arch, not linear. But also, if we're just looking at the equation itself, it doesn't follow our rules because it has an exponent. So this is not linear. This one would be linear. So if you have y equals a number, this would actually be a horizontal line. So if I had y equals 4.7, it's a horizontal line. This one is also linear. So if I try to graph this one, see if they have a pi symbol. So if I have pi x, it's a straight line. So this one is linear. This one does not follow our rules because x is alone in the denominator, so it's not linear. And if we wanted to see what that looked like graphed, you have 4 divided by x. That gives us 2 not straight lines, so it's not linear. This one follows our rules, so it's linear. For this one, if you use your distributive property, you have 4 times x and 4 times -1. You would have 4x minus 4. There's no exponents, nothing really special about this one, so this one is, this one is linear. This one right here is also linear. So if we look at it graphed, you have 5y equals 2x. Still linear, still gives us a straight line. Again, this one follows all of our rules, so it's linear. We've already seen one that looks like this, and we already know that it's going to give us a straight line, so it's linear. This one is not linear because you can't have x times y. You can't have one variable times another variable. So if we look at that, if you have 5xy equals 2, again, that gives us kind of 2 corners. So it's not linear. Let's check and see if this one is linear. So we have y plus x equals 4x plus 5. So this one still gives us a straight line. And another way we could look at this is like solving equations. So if I subtracted x from both sides, those cancel out, then I get y equals 3x plus 5. So it's the same thing, but it puts it in that form of y equals mx plus b. So if we look at graphing this one, you have y equals 3x plus 5. They line up with each other, which means it's the same line. Here, this one breaks our rule because it has an exponent, so it is not linear. This one makes two curves, so it's not linear. This one gives me one straight line, so it's linear. This gives me a straight line down and then a straight line up. So yes, it's straight lines, but it's not the same straight line, so it's not linear. This one gives me kind of an upside down U or a frowny face, so it's not linear. Again, this gives me two different straight lines, so it's not linear. Here we just have some squiggles, obviously not straight lines, so it's not linear. Again, a V is not one straight line, so it's not linear. Here I have a vector, so it only goes in one direction. This one is linear. Here we have a straight line, a diagonal line, and then another straight line. Not all the same line, so it's not linear. So now we're going to look at our rate of change. So all across the top, I'm adding 1. Across the bottom, here I add 10. Then I add 2. Then I add 0. And then I add 4. So this one is not a function. So these are the same, but these are not the same. So again, here, all across the top, I'm adding 1. -13 to -10, I'm adding 3. -10 to -7, add 3. -7 to -4, I add 3. And -4 to -1, I add 3. So my change in x is the same, my change in y is the same, which means this is a linear function. If I look across the top, I'm adding 5. -5 to 0, I add 5. 0 to +5, I add 5. 5 to 10, I add 5. 10 to 15, I'm adding 5. So 1 to 3, I add 2. 3 to 5, I add 2. 5 to 7, add 2. 7 to 9, I add 2. So this one is also linear. If I look across the top of this one, I have 2 to 3, I add 1. From 3 to 6, I add 3. 6 to 11, I add 5. 11 to 18, I add 7. So I can already tell this isn't going to be linear, but let's look across the bottom. So from 0 to 1, I add 1. I add 1. Add 1. And add 1. So this is not linear because my x values are not all the same, but my y values are. So across the top, I add 1. -2 to -1, add 1. 1 to 0, add 1. 0 to 1, add 1. So it might be linear. Let's look at the bottom. -7 to -5, I add 2. -5 to -3, add 2. -3 to -1, add 2. -1 to +1, I add 2. So this is linear. All right, so across the top, I'm adding 1 all the way across. Just going to put a big +1 all the way across the top. -2 plus 1 is -1. -1 plus 1 is 0. 0 plus 1 is 1. 1 plus 1 is 2. If I'm looking across the bottom, 2.5, I'm subtracting 1.5. 0.5 to 0, I'm just subtracting 0.5. Here I start to add 0.5, and then I add 1.5. So this one is not linear. Looking across the top, I have -2 to 1. To -1, I add 1. -1 to 0, add 1. 0 to 1, add 1. 1 to 2, add 1. 8 to 2, I'm subtracting 6. 2 to 0, I'm subtracting 2. 0 to 2, I'm adding 2. 2 to 8, I'm adding 6. So again, this one is not linear because my y values are not the same. If I look across the top, from each x to the other, it's +1. At the bottom, I have -4 to -1, I add 3. -1 to 2, I add 3. 2 to 5, I add 3. 5 to 8, I add 3. So my x's are the same, my y's are the same. So this is linear. All right, so we'll stop there for this video. So this is linear and nonlinear.